To understand how and when tasks are executed, let's take a closer look at the scheduler. The scheduler has multiple responsibilities: parsing DAG files and storing extracted information in the database, determining which tasks are ready to execute and placing these in the queued state, fetching and executing tasks in the queued state. Airflow runs all tasks in DAGs within a job. Although job classes are internal to Airflow, you can view the running jobs in the Airflow UI. The scheduler also runs in a job, albeit its own special job, namely a scheduler job. All jobs can be inspected in the Airflow UI under Browse, Jobs, Figure 12.3. The scheduler job has 3 responsibilities. First, it's responsible for parsing DAG files and storing extracted information in the database. Let's inspect what that entails. The DAG processor. The Airflow scheduler periodically processes Python files in the DAGs directory, the directory set by airflow_core_dags_folder. This means that even if no change was made to a DAG file, it periodically evaluates each DAG file and persists the found DAGs in the Airflow metastore, because you can create dynamic DAGs that change structure based on an external source in Airflow while the code stays the same. An example is a DAG in which a YAML file is read and tasks are generated based on the content of it. In order to pick up changes in dynamic DAGs, the scheduler reprocesses DAG files periodically. Footnote 1. While there are ongoing discussions in the Airflow community to make the DAG parsing event-based by listening for file changes on DAG files and explicitly configuring DAGs for reprocessing if required, which could alleviate the CPU usage of the scheduler, this does not exist at the time of writing. Processing DAGs takes processing power. The more you reprocess your DAG files, the faster changes will be picked up, but at the cost of taking more CPU power. If you know your DAGs do not change dynamically, it's safe to raise default interviews to alleviate the CPU. The interval of DAG processing is related to 4 configurations, shown in Table 12.2. An optimal configuration for your system depends on the number of DAGs, the size of your DAGs, that is, how long it takes for the DAG processor to evaluate them, and the available resources on the machine on which the scheduler is running. All intervals define a boundary for how often to perform a process. At times, the interval value is compared, but it's possible, for example, that the DAG_dir_list_interval is checked after 305 seconds while the value is set to 300 seconds. Airflow_scheduler_dag_dir_list_interval is particularly useful to lower. If you find yourself often adding new DAGs and waiting for them to appear, the issue can be addressed by lowering this value. All DAG processing happens within a while-true loop, in which Airflow loops over a series of steps for processing DAG files over and over. In the log files, you will see the output of DAG processing in /logs/dag_processor_manager/dag_processor_manager.log. Note that these file processing stats are not printed with every iteration, but every X number of seconds that Airflow_scheduler_print_stats_interval is set to. Default, 30 seconds. Also note that the displayed statistics represent the information from the last run, not the results of the last number of print_stats_interval seconds. The task scheduler. Second, the scheduler is responsible for determining which task instances may be executed. A while true loop periodically checks for each task instance if a set of conditions are met, such as, among others, if all upstream dependencies are satisfied, if the end of an interval is reached, if the task instance in the previous DAG ran successfully, if depends_on_past equals true, and so on. Whenever a task instance meets all conditions, it is set to a scheduled state, which means the scheduler decided it met all conditions and is okay to execute. Another loop in the scheduler determines another set of conditions in which tasks go from a scheduled to a queued state. Here, conditions include, among others, if there are enough open slots and if certain tasks have priority over others, given the priority_wait argument. Once all these conditions have been met, the scheduler will push a command to a queue to run the task and set the state of the task instance to queued. This means once the task instance has been placed on a queue, it's no longer the responsibility of the scheduler. At this point, tasks are now the responsibility of the executor that will read the task instance from the queue and start the task on a worker. Note: the task scheduler is responsible for tasks up to the queued state. Once a task is given the queued state, it becomes the responsibility of the executor to run the task. The type of queue and how a task instance is processed once it's been placed on a queue is contained in the process named executor. The executor part of the scheduler can be configured in various ways, from a single process on a single machine to multiple processes distributed over multiple machines, as explained in section 12.1.1. The task executor. In general, the task executor process will wait for the task scheduler process to place task instances to execute on a queue. Once placed in this queue, the executor will fetch the task instance from the queue and execute it. Airflow registers each state change in the metastore. The message placed on the queue contains several details of the task instance. In the executor, executing tasks means creating a new process for the task to run in so that it doesn't bring down Airflow if something fails. In the new process, it executes the CLI command airflow tasks run to run a single task instance, such as the following example, using the local executor. Right before executing the command, Airflow registers the state of the task instance as running in the metastore. After this, it executes the task and periodically checks in by sending a heartbeat to the metastore. The heartbeat is yet another while true loop in which Airflow does the following. Checks if the task has finished. If finished and the exit code is 0, the task is successful. If finished and the exit code does not equal 0, the task failed. If not finished, register the heartbeat and wait X seconds, configured with airflow_scheduler_job_heartbeat_sec, default 5. Repeat. For a successful task, this process repeats a certain number of times until the task is completed. If no error occurred, the state of the task is changed to success. The ideal flow of a task is depicted in figure 12.4. Section 12.2. Installing each executor. There are many ways to install and configure Airflow, hence, it's impractical to elaborate on all ways in this book. However, we demonstrate the main items required for getting each executor up and running. As explained in section 12.1, the executor is part of Airflow's scheduler. The DAG processor and task scheduler can only be run in a single way, by starting Airflow scheduler. However, the task executor can be installed in different ways, from a single process on a single machine to multiple processes on multiple machines for performance and/or redundancy. The executor type is set in Airflow with Airflow_core_executor, where the value is one of the following. Sequential executor, default. Local executor. Celery executor. Kubernetes executor. You can validate the correct installation of any executor by running a DAG. If any task makes it to the running state, it means it went through the cycle of being scheduled, queued, and running, which means it is picked up by the executor. Section 12.2.1. Setting up the sequential executor. The default executor in Airflow is the sequential executor, figure 12.5. The task executor part of the scheduler is run in a single subprocess, within which tasks are run one by one, so it's the slowest method of task execution. However, it is convenient for testing because it requires no configuration. The sequential executor works with a SQLite database. Running Airflow DB init without any configuration will initialize a SQLite database in your $Airflow_home directory, which is a single file named airflow.db. After that, start two processes. Airflow Scheduler, Airflow Web Server. Section 12.2.2. Setting up the local executor. Setting up Airflow with the local executor is not much different from the sequential executor setup, figure 12.6. Its architecture is similar to the sequential executor, but with multiple subprocesses, so tasks can be executed in parallel, and thus it performs faster. Each subprocess executes one task, and subprocesses can run in parallel. Also, the sequential executor is coupled to a SQLite database, while all other executors can work with more sophisticated databases such as MySQL and PostgreSQL, resulting in better performance. To configure the local executor, set airflow_core_executor to local executor. The scheduler can spawn a maximum number of subprocesses configured by airflow_core_parallelism, default 32. Technically, these are not new processes, but rather processes forked from the parent, scheduler process. There are other ways to limit the number of parallel tasks, for example, by lowering the default pool size, airflow_core_dag_concurrency, or airflow_max_active_runs_per_dag. Database-wise, install Airflow with the extra dependencies for the corresponding database system. MySQL, pip install Apache Airflow MySQL. PostgreSQL, pip install Apache Airflow Postgres. The local executor is easy to set up and can get you decent performance. The system is limited by the resources of the scheduler's machine. Once the local executor no longer suffices, for example, in terms of performance or redundancy, the Celery executor and Kubernetes executor, which we address in sections 12.2.3 and 12.2.4 respectively, are the logical next steps. Section 12.2.3. Setting up the Celery executor. The Celery executor is built on top of the Celery project. Celery provides a framework for distributing messages to workers via a queuing system, figure 12.7. As you can see in figure 12.7, both the scheduler and Celery workers require access to both the DAGs and the database. For the database, this is not a problem since you can connect to it with a client. For the DAGs folder, this can be challenging to set up. You make the DAGs available to all machines either via a shared file system or by building a containerized setup where the DAGs are built into an image with Airflow. In the containerized setup, any change to the DAG code will result in a redeployment of the software. To get started with Celery, first install Airflow with the Celery extra dependencies and configure the executor. pip install apache-airflow *Celery Airflow_core_executor equals Celery executor. The queuing system can be anything that Celery supports, which is Redis, RabbitMQ, and AWS SQS at the time of writing. In Celery, the queue is called broker. Installing a broker is not in the scope of this book, but after installation, you must configure Airflow to the broker by setting airflow_celery_broker_URL. Redis, this. RabbitMQ, this. Check the documentation for your queuing system for the corresponding URI format. The broker_URL allows the scheduler to send messages to the queue. For the Celery workers to communicate with the Airflow metastore, we must also configure Airflow_Celery_result_backend. In Celery, the prefix DB+ is used to indicate a database connection. MySQL, this. PostgreSQL, this. Ensure the DAGs folder is also accessible on the worker machines on the same path, as configured by airflow_core_dags_folder. After this, we should be good to go. 1. Start Airflow Web Server. 2. Start Airflow Scheduler. 3. Start Airflow Celery Worker. Airflow Celery Worker is a small wrapper command starting a Celery worker. All should be up and running now. Note: To validate the installation, you could manually trigger a DAG. If any task completes successfully, it will have gone through all components of the Celery executor setup, meaning everything works as intended. To monitor the status of the system, we can set up Flower, a web-based monitoring tool for Celery, in which we can inspect, among others, workers, tasks, and the status of the whole Celery system. The Airflow CLI also provides a convenience command to start Flower: Airflow Celery Flower. By default, Flower runs on port 5555. After starting, browse to this, figure 12.8. In the first view of Flower, we see the number of registered Celery workers, their status, and some high-level information on the number of tasks each worker has processed. How can you tell if the system is performing well? The most useful graphic in the Flower interface is the monitor page in figure 12.9, which shows the status of the system in a few graphs. From the two distributed executor modes Airflow offers, Celery and Kubernetes, the Celery executor is the easiest to set up from scratch because you only need to set up one additional component, the queue. The Celery workers and Flower dashboard are integrated into Airflow, which makes it easy to set up and scale the execution of tasks over multiple machines. Section 12.2.4. Setting up the Kubernetes executor. Last but not least is the Kubernetes executor. Set Airflow_core_executor equals Kubernetes executor to use it. As the name implies, this executor type is coupled to Kubernetes, which is the most used system for running and managing software in containers. Many companies run their software on Kubernetes, since containers provide an isolated environment that ensures what you develop on your computer runs the same on the production system. Thus, the Airflow community expressed a strong desire to run Airflow on Kubernetes. Architecturally, the Kubernetes executor looks like figure 12.10. When working with the Kubernetes executor, it helps to have prior knowledge of Kubernetes. Kubernetes can be large and complex. However, the Airflow Kubernetes executor only uses a small part of all available components on the Kubernetes platform. For now, it's good to know a pod is the smallest unit of work in Kubernetes and can run one or more containers. In the context of Airflow, one task will run in one pod. A pod is created every time a task is executed. When the scheduler decides to run a task, it sends a pod creation request to the Kubernetes API, which then creates a pod running an Airflow container with the command airflow tasks run, as shown in listing 12.3. Disregarding several details. Kubernetes itself monitors the status of the pod. With the other executor setups, there was a clear separation between physical machines. With Kubernetes, all processes run in pods, where they can be distributed over multiple machines, although they might also be running on the same machine. From a user's perspective, processes run in pods, and the user does not know of underlying machines. The most used way to deploy software on Kubernetes is with Helm, a package manager for Kubernetes. Various third-party Helm charts for Airflow are available on Helm Hub, the repository for Helm charts. At the time of writing, an official Airflow Helm chart is available on the master branch of the Airflow project. However, it is not yet available on public Helm repositories at the time of writing. The minimal installation instructions are therefore, assuming a functioning Kubernetes cluster and Helm 3+, as follows. One of the trickier parts of setting up the Kubernetes executor is determining how to distribute DAG files between Airflow processes. There are three methods for this. 1. Share DAGs between pods with a persistent volume. 2. Pull the latest DAG code from a repository with a git sync init container. 3. Build the DAGs into the Docker image. First, let's establish how to deploy Airflow DAG code without using containers. All Airflow processes must have access to a directory containing DAG files. On a single machine, this isn't too hard. Start all Airflow processes and point to the directory on the machine holding the DAG code. However, it becomes difficult when running Airflow processes on different machines. In that case, you need some way to make DAG code accessible by both machines, such as a shared file system, figure 12.11. However, getting code on a shared file system is not a trivial task. A file system is built for storing and retrieving files on a storage medium, not for providing an interface to the internet for easy file exchange. The exchange of files over the internet would be handled by an application running on the same machine as the file system is mounted to. In more practical words, say you have a shared file system such as NFS, Network File System, to share files between the Airflow scheduler and worker machines. You develop code on your development machine, but cannot copy files directly to the NFS file system because it does not have an interface to the internet. To copy your files onto the NFS, it must be mounted to a machine, and files must be written onto it via an application running on the same machine, such as FTP. Figure 12.12. In Figure 12.12, a developer or CI/CD system can push Airflow code to the Airflow system via an FTP server, which runs on one of the Airflow machines. Via the FTP server, the NFS volume should be made accessible for the CI/CD system to push DAG files to and make it accessible to all Airflow machines. What if a pushing mechanism for the CI/CD system is not an option? This is a common challenge for various reasons, such as security or network limitations. In that case, an often seen solution is to pull the code in from an Airflow machine via a DAG named the DAG puller DAG. With the DAG puller DAG, the latest code from the master branch is pulled onto the Airflow machine every 5 minutes. Figure 12.13. This obviously imposes a delay between the code on the master branch and the deployment of the code in Airflow, but it's sometimes the most practical solution. Now that we know the challenges and potential solutions for deploying DAGs running Airflow in a distributed setup, let's see how to share DAGs between pods in Kubernetes. Share DAGs between pods with a persistent volume. Persistent volumes are Kubernetes abstraction over storage and allow mounting shared volumes to containers without having to know the underlying storage technology, such as NFS, Azure File Storage, or AWS EBS. One of the trickier parts is to set up a CI/CD pipeline where DAG code is pushed to the shared volume, which typically does not provide out-of-the-box functionality for pushing directly to the shared volume. To enable sharing DAGs with a persistent volume, set the configuration item airflow_kubernetes_dags_volume_claim to the name of the volume claim in Kubernetes, on the Airflow pod. DAG code must be copied to the volume, either with a pushing method, as shown in Figure 12.12, or a pulling method, as shown in Listing 12.5. The solution might depend on your chosen volume type, so refer to the Kubernetes documentation on volumes for more information. Pull the latest DAG code from a repository with a git sync init container. The Airflow configuration holds a list of settings for pulling a Git repository via a sidecar container before running an Airflow task, not complete. See these settings. While not all details are necessary to fill, setting the git_repo and credentials, user plus password, or git_ssh_key_secret_name will enable the git sync. Airflow will create a sync container that pulls the code from the configured repository before starting a task. Build the DAGs into the Docker image. Lastly, building the DAG files into the Airflow image is also a popular option for its immutability. Any change to DAG files results in the build and deployment of a new Docker image, so that you are always certain which version of your code you are running on. To tell the Kubernetes executor you've built DAG files into the image, set airflow_kubernetes_dags_in_image equals true. The build and deployment process becomes a little different. Figure 12.14. Building an Airflow image together with DAG code provides several benefits. We are certain which version of the code is currently deployed. We can run the same Airflow environment locally as on production. Conflicts between new dependencies are found at build time, not at runtime. If we zoom in on the build, for performance it's preferable to install Airflow and add your DAG code in two separate steps. 1. Installation dependencies. 2. Add only DAG code. The reason for this split is that Airflow contains lots of dependencies, which can take in the order of minutes to build. You probably will not change dependencies often during deployment, but will mostly change DAG code. To avoid reinstalling dependencies with every small change, copy your DAG code into the image in a separate step. If your CI/CD system caches Docker layers, this could be in a separate Docker statement, because you can retrieve the base layers quickly. If your CI/CD system does not cache Docker layers, it's wise to build one base image for Airflow and dependencies and a second image for adding only the DAG code. Let's illustrate how the latter option works with two Docker files. First is the base Docker file. Footnote 2. Both Docker files are meant for demonstration purposes. This base Docker file starts with the official Airflow 2.0.0 Docker image and installs additional dependencies listed in requirements.txt. Having a separate file for additional dependencies simplifies the CI/CD pipeline, since any change to requirements.txt should always trigger a rebuild of the base image. This command will build the base image. Having a pre-built base image with all dependencies makes building the final image a very fast process, since the only step required is copying the DAG files. Use the command docker build-t myrepo/airflow to build it. However, this image will be built with every single change. Depending on the dependencies you're installing, the difference in time between building the base and final image can be very large. By splitting the build process of an Airflow Docker image into either separate statements or separate images, we can significantly speed up the build time, because only the files changed most often, the DAG scripts, are copied into the Docker image. A more time-consuming full rebuild of the Docker image will be performed only when needed. From the Kubernetes side, ensure your Airflow image tag is defined in the YAML by Airflow_Kubernetes_pod_template_file, or make sure Airflow_Kubernetes_worker_container_tag is set to the tag you want the worker pods to deploy. If using the Airflow Helm chart, you can update the deployed version with the Helm CLI by setting the tag of the newly built image. Section 12.3. Capturing logs of all Airflow processes. What about logging? All systems produce some sort of output, and at times we want to know what's going on. In Airflow, there are three types of logs. Web server logs. These hold information on web activity, that is, which requests are sent to the web server. Scheduler logs. These hold information on all scheduler activity, which includes DAG parsing, scheduling tasks, and more. Task logs. These hold the logs of one single task instance in each log file. By default, logs are written in $Airflow_home/logs on the local file system. Logging is configurable in various ways. In this section, we will demonstrate the default logging behavior, plus how to write logs to a remote storage system in Section 12.3.4. Section 12.3.1. Capturing the web server output. The web server serves static files, and every request to a file is displayed in the web server output. See the following example. When starting the web server on the command line, you will see this output printed to standard out or standard error. What if you want to preserve logs after the web server shuts down? Within the web server, there are two types of logs: access logs, as shown, and error logs, which hold not only errors, but also system information, such as the following. See these logs. Both types of logs can be written to a file by providing a flag when starting Airflow web server. Airflow web server-access_log file, file name. Airflow web server-error_log file, file name. The file name will be relative to airflow_home, so setting accesslogs.log as the file name, for example, will create a file like this. Section 12.3.2, Capturing the Scheduler Output. The scheduler does write logs to files by default, as opposed to the web server. Looking at the $airflow_home/logs directory again, we see various files related to scheduler logs. This directory tree is the result of processing two DAGs, hello_world and second_DAG. Every time the scheduler processes a DAG file, several lines are written to the respective file. These lines are key to understanding how the scheduler operates. Let's look at hello_world.py.log. These steps of processing a DAG file, loading the DAG object from the file, and checking if many conditions are met, such as DAG schedulers, are executed many times over and are part of the core functionality of the scheduler. From these logs, we can derive whether the scheduler is working as intended. There is also a single file named dag_processor_manager.log. Log rotation is performed once it reaches 100 megabytes, in which an aggregated view, default last 30 seconds, is displayed of which files the scheduler has processed, listing 12.2. Section 12.3.3. Capturing task logs. Lastly, we have task logs, where each file represents one attempt of one task. The contents of these files reflect what we see when opening a task in the web server UI. Section 12.3.4. Sending logs to remote storage. Depending on your Airflow setup, you might want to send logs elsewhere. For example, when running Airflow in ephemeral containers in which logs are gone when the container stops, or for archival purposes. Airflow holds a feature named remote logging, which allows us to ship logs to a remote system. At the time of writing, the following remote systems are supported. AWS S3 requires pip install Apache-Airflow, Amazon. Azure Blob Storage requires pip install Apache-Airflow, Microsoft.Azure. Elasticsearch requires pip install Apache-Airflow, Elasticsearch. Google Cloud Storage requires pip install Apache-Airflow, Google. To configure Airflow for remote logging, set the following configurations. Airflow_core_remote_logging equals true. Airflow_core_remote_log_con_ID equals ellipsis. The remote_log_con_ID points to the ID of the connection holding the credentials to your remote system. After this, each remote logging system can read configurations specific to that system. For example, the path to which logs should be written in Google Cloud Storage can be configured as this. Refer to the Airflow documentation for the details for each system. Section 12.4. Visualizing and monitoring Airflow metrics. At some point, you might want to know more about the performance of your Airflow setup. In this section, we focus on numerical data about the status of the system, called metrics. For example, the number of seconds delay between queuing a task and the actual execution of the task. In monitoring literature, observability and full understanding of a system are achieved by a combination of three items: logs, metrics, and traces. Logs, textual data, are covered in section 12.3. We cover metrics in this section, and tracing is not in the scope of this book. Each Airflow setup has its own characteristics. Some installations are big, some are small. Some have few DAGs and many tasks. Some have many DAGs with only a few tasks. It's impractical to cover every possible situation in a book, so we demonstrate the main ideas for monitoring Airflow, which should apply to any installation. The end goal is to get started with collecting metrics about your setup and actively using these to your advantage, such as with a dashboard, figure 12.15. Section 12.4.1. Collecting metrics from Airflow. Airflow is instrumented with stats-d. See this link. What does it mean to be instrumented? Instrumented in the context of stats-d and Airflow means certain events in Airflow result in information about the event being sent so that it can be collected, aggregated, and visualized or reported. For example, whenever a task fails, an event named TI_failures is sent with a value of 1, meaning one task failure occurred. Pushing versus pulling. When comparing metrics systems, a common discussion is about pushing versus pulling, or the push versus pull model. With the push model, metrics are sent or pushed to a metrics collection system. With the pull model, metrics are exposed by the system to monitor a certain endpoint, and a metrics collection system must fetch or pull metrics from the system to monitor from the given endpoint. Pushing might result in overflowing the metrics collection system when many systems start pushing many metrics simultaneously to the metrics collection system. Stats-d works with the push model. So, when starting with monitoring in Airflow, we must set up a metrics collection system to which stats-d can push its metrics before we can view the metrics. Which metrics collection system? Stats-d is one of the many available metrics collection systems. Others include Prometheus and Graphite. A Stats-d client is installed with Airflow. However, the server that will collect the metrics is something you have to set up yourself. The Stats-d client communicates metrics to the server in a certain format, and many metrics collection systems can interchange components by reading each other's formats. For example, Prometheus's server can be used for storing metrics from Airflow. However, the metrics are sent in stats-d format, so there must be a translation for Prometheus to understand the metrics. Also, Prometheus applies the pull model, whereas stats-d applies the push model. So some intermediary must be installed to which stats-d can push and Prometheus can pull, because Airflow does not expose Prometheus's metrics format, and thus Prometheus cannot pull metrics directly from Airflow. Why the mixing and matching? Mainly because Prometheus is the tool of choice for metrics collection to many developers and sysadmins. It is used at many companies and prevails over stats-d on many points, such as its flexible data model, ease of operation, and integration with virtually any other system. Therefore, we also prefer Prometheus for dealing with metrics, and we demonstrate how to transform stats-d metrics into Prometheus metrics, after which we can visualize the collected metrics with Grafana. Grafana is a dashboarding tool for visualizing time series data for monitoring purposes.